So as an introduction to the Distribution System Operability Framework, or DSOF for short, this was first published in September 2017, around about the same time as our DSO strategy was launched, and it's been refreshed for 2018 and is constantly being expanded and updated on over time. So to give you a bit of background as to what the DSOF is about, it aims to highlight some of the technical and commercial challenges that are facing distribution network operators as they become distribution system operators in the not too distant future. In the DSOF, we consider a range of issues from network design through to real-time network operation. A key theme throughout the DSOF is the growing role of data capture and analysis in distribution system operation. In the last 10 years, we have seen unprecedented developments in distribution networking, including the growth of distribution connected generation and a major shift in Great Britain's generation mix towards renewables. In addition, advances in control systems and power electronics are providing us with alternatives to conventional reinforcement when managing demand growth and providing new connections. So, in the network strategy team at Western Power Distribution, we are responsible for a number of key outputs and mainly look at the development of the network for the next 5 years and beyond. On the slide there, you can see a number of documents that we have published under our team. Just to highlight a couple of them, the Distribution Future Energy Scenarios and Strategic Investment Options reports, which are the 8 that you can see on the bottom of the screen. These are where we use scenario-based forecasting to assess the growth of demand and generation across each of our license areas in turn over the next 15-year period. And then we apply these scenario-based forecasts onto a network model to identify potential future constraints on our network. Also another few publications that we're involved in. But in general, the DSOF utilizes lots of the learning and technical outputs from our other projects to develop case studies and demonstrate why we think some of these technical issues highlighted may occur in the future. If you are interested in more information about any network strategy publications, they can be found on our website. So the DSOF changes for 2018-19. For those of you that have seen the DSOF as published in 2017, it was quite a large report. And for this year, what we've done is separated it into individual articles to make them a bit more manageable. They still broadly follow the same 3 themes as identified in our innovation strategy. This is assets, network operations, and customers. However, we acknowledge the fact it's difficult to assign each topic to a single category. So this table outlines how many of the different themes each article can impact. When we publish a new or updated article, it's added to the bottom of the table. So you can see the one there for whole system fault level, new for 2019. And if you are on the website updates newsletter for Western Power, you should receive a notification as and when a new article is published. So the next steps for the DSOF, as I said, the whole purpose of the DSOF is to raise the profile of some of the issues facing DNOs and seek solutions from a wider audience, which is hopefully why some of you are listening today. We periodically review each of our articles on a rolling basis and publish new articles as new issues develop. Once we've published the next batch of updated or new articles, we will be holding further webinars subject to interest. So without further ado, I'll pass you over to David Tuffery, who's going to present on changing load profiles.
Hey, sorry about that. We had a few issues with muting. As Ollie just said, I am David Tuffery and I work in the WPD network strategy team. My main roles within the team are focusing on the DFES and the shaping sub-transmission work. So this is taking the outputs from our future energy scenarios and then feeding them into technical analysis and assessing our 132 kV and 66 kV networks. And that's really where this DSOF article on changing load profiles came from. We've had a lot of interesting learning from this process, looking out to 2032 and seeing how load profiles are likely to change under the different scenarios. So just a quick overview of what I'm going to cover today. I'm just going to go through some traditional network design methods and look at demand categorization and the sort of traditional demand and how generations connect in. I'll then move on to look at the generation and demand technologies that we are forecasting will connect to our network and how the impact they may have. I'm going to particularly focus on electric vehicles, heat pumps and battery storage. And then we'll do a little case study and run through the impact it has under one of our higher growth scenarios, and then look at some flexibility options that could be implemented to stop the need for reinforcement, and then finally some solutions and future challenges. So traditionally, distribution networks have been almost entirely designed for demand, whether this is a peak demand or minimum demand where you see sort of voltage issues, voltage constraints. Peak demand normally occurs in winter in early evening, about 6 p.m. Last year was a bit of an exception where we actually saw it in early March due to the beast from the east. And some of the factors that actually impact the network loading are obviously time of day. Ambient temperature plays an important factor because of the heating and cooling aspects, sunlight hour because of lighting, days of the week. We also see major sport events such as sporting events, and with more and more generation connecting, this is really starting to change the loading on the network. And we're not just having to look at demand edge cases to design the distribution network, but also generation days. But saying that, if you actually look at this graph here, which shows the historic peak demand on our Southwest and South Wales licence areas, what we actually see is that there's actually been a general downward trend over the last 10 years, and over the last 20 years there's not actually been much change. So actual extrapolation from this data to actually forecast future demand growth isn't actually a particularly good way to go. So for this reason, we have used the DFES scenarios to actually try and better group everything. If we look here, we've got 3 different demand types, because understanding how demand is coincident is important. So we've got the green line here shows a typical domestic unrestricted profile, something like you'd see in the Elexon class profile 1. And then we've got the purple line showing a nighttime peaking similar to the Elexon class profile 2. And the red is a sort of commercial non-domestic one with a midday peak, and making sure that we understand how these peak, when they peak, and the level of diversity between these is crucial to being able to design the network ahead of need. So yeah, going on to the DFES, we forecast a number of different technology types for generation. These are down to the left in the table, and we forecast these in megawatts. If we look at the demand side, there's all the traditional demand, industrial, commercial, and then we've got electric vehicles and heat pumps, which are 2 that we're particularly interested in, because if they take off like they're forecast to, then it's going to have a significant impact on the network. And then energy storage, in particular batteries, could have a big impact because of its ability to import and export onto the network, and we'll go through those in a bit more detail shortly. So starting with electric vehicles, we've got car sales here. So currently only about 1% of cars sold are electric vehicles, so that's plug-in hybrid or full electric. Under our 4 future energy scenarios, which are the National Grid 2017 FES scenarios, because we lag a year behind currently with our analysis, this is forecast to grow to about 20% under the low growth steady state scenario and just over 70% under the high growth 2 degrees scenario. What does this actually mean in terms of numbers? Well, yeah, at the moment we've got very low levels across our WPD license area. This is going to grow to almost 3 million under the high growth scenario, and under the lower growth is just under 1 million, I think about 800,000. But numbers is only one part of this. Understanding how many electric vehicles there will be in our license area gives us a starting point. But what we need to really understand is how many chargers they're going to be, what battery size, what are the charging profiles going to be? Are people going to be charging these at home? Are they going to be charging them at work, on street parking, fleet charging, etc.? So we'll try and sort of go into these in a bit more detail. So one example of a profile is taken from the customer-led Network Revolution project, which used 143 participants and a 3.5 kilowatt charger. You can see this on your screen. The red line is without any sort of managed charging or time of use tariff, and we can see that even though it's a 3.5 kilowatt charger, there's inherent diversity. So actually, once you're looking at a large enough sample, we're only seeing about a 0.9 kilowatt peak. This peak's occurring at about 8 o'clock at night with significant demand at the time of traditional network peak at about 6. If we look at the blue line, this is with a time of use tariff where customers are incentivized to time shift their charging later, so it doesn't coincide with existing peaks. And this, is still the overall same amount of energy for both of these. It's just time shifted later. We'll come on to it in a bit more detail in the case study shortly. If we look at heat pump growth, we can see we've got about 25,000 connected onto our network currently, and our low growth scenario just sees a very low increase of this up to about 60,000, and this is over 400,000 into higher growth. So for anyone who isn't familiar with a heat pump, it's sort of similar to a refrigerator in the way that it takes heat from a heat source into a heat sink and is powered by electricity. It's got, I think, an efficiency of between about 3 and 4. And if we look at these two graphs here taken from the Electric Northwest Managing the Impact of Electrification and Heat project, we can see that they actually need a backup source of either electricity or gas, because at times of extreme cold, the heat pumps aren't normally sufficient to actually heat a house or domestic property. So the left graph here shows a 3 kilowatt electric peak at time of winter peak, whereas the one on the right, which is a gas backup where it has the ability to switch over to the gas network. WPD's Freedom project looked at this in a lot of detail for anyone that is interested, shows that actually there's no electrical demand at times of winter peak, which is obviously good from a network perspective. It needs the market signals for this to be able to work successfully. So battery storage, we've got sort of very low levels connected currently, but we've got a lot of interest to connect to the distribution network. And there's quite a high divergence here between the scenarios, with under 1 gigawatt under the low growth scenarios and almost 3.5 gigawatts by 2030 under the high growth. So to better understand how batteries are going to work, because there's so few connected, it's hard to actually assess them. We went out for a consultation with Regen, I think in 2017, and they came back with a few different business models, such as response services, reserve services, generation co-location, etc., because they can import and export and operate in different markets. So understanding how they are going to operate and the contractual arrangements that we can have with them, because at the moment we have to assess them as a worst case that they will be operating in a way that's detrimental to the local network, whereas in the future we may be able to actually work with them so that they will be exporting at times of peak demand. So just looking at a couple of examples from this consultation as examples of how they may operate. So you see the evening peak period on the top graph, and this is effectively time shifting to reduce the demand at peak. So they are importing at just before the peak and then exporting at time of peak. And then they could potentially be playing into other markets like frequency response, depending on how the markets develop. The second graph shows a generation peak shaving where there was, say, constraints and batteries were co-located with solar. They could actually, the PV could charge the batteries and then that could export onto the network later where there weren't the same constraints. So obviously we've focused mainly on demand so far, but generation is playing an important part of network loading. And what we're seeing, so this is for the Southwest, which is our latest DFES analysis area. We've got just over 2 gigawatts of generation connected, and under the high growth scenario, this is forecast to go up to almost 6 gigawatts, with a significant amount being solar. So yeah, I'll try and hopefully running through a case study here will represent this a bit better. So we've got a BSP from our southwest license area, a bulk supply point, a 132 kV to 33 kV substation. If you look at the figure on this slide, what you see is a representation of the peak demand profile at winter peak. So this is just under 100 megawatts currently. It's supplied by two 45 90 MVA transformers with a cycle rating 117 MVA. So for next fault, it's comfortably within its rating. Under our scenarios, by 2030, under the high growth, just to represent so it's a bit easier to see, what you can see is that this actually increases to 158 megawatts. Something that's worth bearing in mind is the yellow hashed area at the top is showing a battery constantly exporting. We appreciate this is not how a battery would actually operate, but from a design perspective, until we have confidence that they will be operating in a way beneficial to the network, we need to assume that they will be importing at times of demand and exporting at times of peak generation. So overall, there's been about a 42% overall increase in energy requirements. But traditionally this will require a reinforcement as the rating was only 170 MVA. But if we look at some of the flexibility options and how this is going to further change the load profile, so as we discussed, time of use tariffs or managed electric vehicle charging to time shift that energy from peak away into the sort of early morning, late evening. This purple hashed area shows the reduction in energy and where it's time shifted to between midnight and 6 a.m. Again, still the same amount of energy under the graph. And then we can also start considering generation once the contractual arrangements are there. So if we ignore intermittent generation, which can't be relied on hence because it's intermittent, and focus on the non-intermittent generation and storage and see what impact that can have. So what we've got here is the top orange line is the profile from with time of use tariffs on the electric vehicles with batteries exporting for the entire period, or that is what it's representing. And then what we've got is the blue line, which is largely hidden below the dark red line, is if batteries were just assumed to be doing nothing. And then if we could take that one step further and we could actually contract with all 9.5 megawatts of batteries for them to time shift at peak demand, we see that there's actually a further 10 megawatt reduction. And depending on what markets they're playing into, they may in reality be importing and exporting multiple times of the day. The non-intermittent generation, same again. If we could contract with the generators, we could see about a 22 megawatt reduction in the overall peak demand from a BSP perspective. So what does that look like once you put them all together? So from operating the network completely passively, where the demand is about 158 megawatts, we've reduced this down to about 118 megawatts. Which we appreciate. This is just trying to represent the possibility that you could contract with all of this. In reality, some of the non-intermittent generation we may not be able to contract with because it's playing for other services, or the batteries may be co-located and already utilized, but it's showing the ability with flexibility to change the loading on the network significantly, unlike with a passive network. One thing that's worth pointing out here is you can see that the loads curve has significantly flattened at the BSP, and asset ratings assume that there is a cyclic nature to a lot of the loading. So what we may need to do is look at reassessing ratings, as flexibility means that the utilization of assets increase. So in terms of impact, I think we've gone through a lot of this, but there is a point where flexibility is either not possible because technically there's not the flexibility available, or it gets to a point where flexibility isn't the best cost option and just traditional reinforcement of putting copper in the ground, additional transformers, is the best. So what are WPD doing to ensure that we are forecasting this best we can and understanding? So we are obviously doing our DFES scenarios and our shaping sub-transmission work to try and identify any potential issues ahead of need, and then looking at potential reinforcement solutions or flexibility options. And whilst we're forecasting numbers, as I hope you've gathered from this presentation, it's not just numbers we need, but it's understanding how these emerging technologies and profiles are actually going to operate. So we've got a few projects that we're currently running, like Electric Nation, which has 600 participants looking at domestic profiles of chargers with 7 kilowatt chargers, and we're getting a lot of information out of that, which we're going to look to feed into our analysis. Freedom, as I mentioned earlier, is looking at, or has looked at, hybrid heat pumps and how they can transition the energy requirement onto the gas network at times of high demand. And demand side response is looking at the ability to use flexibility to alter loading to reduce the requirement for traditional reinforcement. We're also looking to transition away from our edge case time series analysis to more of an energy assessment. So just some future challenges for you to think about. Yeah, whilst we are getting there with our electric vehicle domestic charging, this is only people charging at their home. We still need a much better understanding about how fleet vehicles are going to charge, if HGVs and LGVs have a large uptake, sort of bus fleets, etc. So the more information and projects that go on with this, the better. The same sort of thing with storage. There's still relatively small amounts connected, so the more we can understand about how they're going to operate, the easier it is to design the network. Monitoring is going to become more important at the lower voltage levels, where we need to understand what's going on with all of these heat pumps and electric vehicles connecting down at the LV, where we've currently got limited visibility. And we also need to look at assessing at what point do you move away from flexibility towards reinforcement and the flexibility contractual arrangements with things like batteries and non-intermittent generation. So that is pretty much all I've got to say. I think I'm going to pass over to my colleague Clive now, who's going to talk about our fault level DSOF article.
Thank you, David. My name's Clive Goodman. I'm one of the network strategy team, and I'm going to cover the topic of fault level management. Just a summary of where 2017 DSOF left us. The last DSOF highlighted the impact on fault levels due to the shift in generation mix from large synchronous transmission connected generation to smaller scale non-synchronous units connected to the distribution system, an increase in generation using power electronic converter interfaces such as things like solar PV, producing lower fault currents compared to rotating machines, and the increase in the average steady state fault levels on the distribution network. And we highlighted that fault levels need to be carefully managed to ensure safety, correct operation of protection schemes, and provide a high level of power quality. So with the support of the Electricity Networks Association Open Network Project, a working group was set up between National Grid ESO, Scottish Power Energy Networks, Electricity Northwest and Western Power Distribution to examine the interaction of the decline in synchronous transmission connected generation capacity and an increase in non-synchronous generation and the impact on the whole system fault levels. Historically, the short circuit level contribution to the distribution network has come from the transmission side, this being predominantly from large synchronous generators. In recent years, the increase in non-synchronous generation has caused and will cause the transmission system to operate at lower short circuit levels more frequently. The increase in distribution system connected generation will increase the contribution to the short circuit level on the distribution system, and if the short circuit level is too low or not sustained, protection systems may not operate correctly. So for our analysis, we took 4 typical network configurations between transmission and distribution voltage levels, 4 there as shown, and we used an impedance-based model to simulate the transmission in feed, the grid transformer subsystem, along with the distribution system demand, and then the generation both from synchronous and non-synchronous generation. We had hourly transmission fault level in feeds for 3 sample years, 2018, which is effectively now 2022 and 2027. And that was based upon the transmission generation and demand dispatch for a sample area with a high non-synchronous generation output. We assume the short circuit level contribution from demand would be 1 per unit per MVA on the the demand to stay the same across the 3 years we were examining. The synchronous transmission in feed we assumed to be 5 per unit per MVA on the LV bus bar, and the non-synchronous generation in feeds were varied from 0 per unit minimum to 1.5 per unit as a maximum. So this graph shows effectively the inputs from the short circuit level from the transmission system, and it shows the three years we looked at, and the short circuit level. If you looked at the short circuit level in 2027, has a far wider variation than it does in 2018, and also there is a decline, and there will be longer periods in 2017 when the fault level will be at a lower level. So looking at the impact of non-synchronous generation at the distribution system level. So this is looking at the distribution bus bar. There's a reduction in the short circuit level in 2027 compared to 2018, and there's also a wider variation. The purple line shows a wider variation in 2027. Likewise, the impact of the non-synchronous generation on the maximum short circuit level at the distribution level. Similar curves here, and again, there's a wider variation in 2027 in comparison with 2018. There's also an increase in the short circuit levels in 2027 compared to 2018. So we then looked at the proportion of fault current from the transmission system coming over onto the distribution system, and we've got 4 curves there. The dotted lines are showing the ones where we're modelling the maximum distribution fault in feed, and the solid lines are the minimum ones, and that shows that by 2027 the proportion of short circuit current coming from the transmission system towards the distribution system is decreasing, and that is due to the growth in generation on the distribution system and a decline on the transmission system. So we had a look at the sensitivity in terms of an increase or decrease on the transmission system, and how that is then mirrored in the distribution system through the transformer. And our results showed that for a 50% decrease in the transmission short circuit level only results in a 15% decrease on the distribution system or distribution bus bar short circuit level. then went on to look at the impact of distribution short circuit level on the transmission network, and not surprisingly, the growth in distributed transmission was increasing the maximum fault level contribution from the distribution system over to the transmission system, and the growth in demand and distributed generation will slightly increase the fault in feed from the distribution network. And we've got similar curves there where the dotted lines show the when we've modeled the maximum in feed from non-synchronous generation. We also had a look at the seasonal variation in short circuit level. I've just included a couple of graphs here. The report has far more detail of this. So to conclude, our conclusions were transmission system fault levels in future years are expected to stay at lower levels for longer periods. Decline in transmission fault levels will lead to a reduction in the minimum distribution fault level. The increase in maximum distribution fault at times of peak demand due to growth in demand and distributed generation. There'll be a decrease in the proportional contribution of transmission short circuit levels towards maximum distribution short circuit levels. A minimal change in the proportional contribution of transmission short circuit level towards minimum distribution short circuit level. And then there'll be an increase in the proportional contribution of distribution short circuit level towards maximum and minimum transmission short circuit level. The variations of these levels within a day and within a year will require moving away from using peak or average in-feed values that we've traditionally used for analysis. And the existing inverter-based technologies aren't necessarily reliable in providing sustained levels of fault current and should be ignored for the minimum short circuit level calculations. So moving forward, the future considerations are likely to be that distribution short circuit levels will become more important to the transmission system in the future. Enhanced understanding of how the transmission and distribution networks perform and interact in varying year-to-year conditions, particularly minimum conditions, is going to be more important. The existing industry guidelines tend to focus on peak network conditions. That's something that may need to be looked at, and the need to improve and enhance standards to provide guidance on minimum network conditions. So that sort of concludes my presentation, and thank you.
Hi, afternoon everyone. So as the slide says, I'm John Berry and I'm part of WPD's innovation team, and I wanted to spend a few moments going through our recently released NIA call for 2019. So discussing the 4 challenges. So I'll briefly touch on the topics you can see on the screen as part of the agenda, a brief introduction, touching on our wider innovation program through different funding mechanisms and some of the projects that we've got. Some of you may be familiar that we ran an NIA call last year, and we also recently concluded an NIC call through the ENA, and touch on a little bit about our innovation strategy and the future challenges, and then more detail on our 4 challenges this year for the NIA call. And hopefully you'll see some overlap with what's been discussed earlier today and what we're looking for in terms of challenges and solving those as projects going forwards. So this is a overview slide of our Future Networks program. It cuts across the same themes as part of the DSOF document, the assets, customers and operations, and below we can see a split of our generally NIA funded projects, Network Innovation Allowance, and some of our larger projects at the top funded through the Network Innovation Competition and previous low carbon network funds. So it's been discussed earlier about the 3 themes and how they cut across, so I won't touch too much on that. Wanted to give a brief update on the NIA third-party call that we ran last year. So last year we had this very closely aligned to the DSOF document that was released last year, and specifically the 9 articles, 3 split across each of those themes. Again, assets, network, operations, and customers. And we received over 80 submissions at different time through the process, roughly equal between assets, customers, and operations. And we got a really good response from some of the large companies and some small SMEs and university institutions. And through that process, we, through the review and what was suitable to be taken forward as NIA projects, we've now got 8 live NIA projects. So wanted to provide a bit of an overview about the value of participating in these calls and them being taken through to live projects. And we've got 8, and for more information, you can look on our Smarter Networks portal or our WPD Innovation website. So briefly touch on our overarching themes. So as well as our own innovation strategy that looks at our three core themes and areas and prioritizes our focus, there's also the wider ENA electricity innovation strategy. And on the screen are the 5 themes for the challenges. So there's network improvements and system operability, transition to a low carbon future, new technologies and commercial evolution, customer and stakeholder focus, safety, health and environment. And much like our asset operations and customers, there's much overlap between these 5 themes. And when we share the slides, the 2 links will be able to take you straight to those documents if you want any more information. And then touching on specifically the ENA future challenges around the 3 themes, put onto times up to 2019, so look at facilitating change, 19 to 22, looking at smarter networks, and then concentrating on whole systems from 2022 out. So hopefully when I discuss in a little bit more detail the 4 themes, the 4 project challenges, you'll see that lots of those are around facilitating change. So looking at how we develop solutions, interact with customers, EV charging requirements, and then specifically development of safer and efficient working practices. So the specific 4 themes, 4 challenges that we have are robot trades, on-street EV charging, advanced fault level monitor, and public charging infrastructure. So I don't propose to read through the slides, but just to give a general overview of the 4 challenges that we're looking for. So firstly, the robot trades. Obviously, working in the electricity industry, we're always looking for safer and more efficient ways of operation. And as part of this challenge, we're looking to see if we can look at using robotic or automated technologies to identify, locate faults on the network, and see what we can do, all the way from finding faults, exposing and digging into the ground, to preparing for restorative works to be carried out. We're really interested in what we can do with these robots, automated machines, to take away humans from the point of interaction with potential live electricity. So that's the overview for that. On-street EV charging, it was spoken before about the potential take-ups across the 4 different scenarios. Obviously, specifics in the UK, there's lots of domestic properties and other environments where on-street parking is a must. And what we're looking for as part of this is how do we develop suitable infrastructure to enable this on-street parking. So through to advanced technologies in terms of the specific charging point, connectivity of the vehicle to that, so we don't end up with trailing leads across pavements and such things like that, through to smaller form factor technologies such as transformers, switchgear and such, where if we're looking at needing to do reinforcement to increase the capacity of our network, how can we integrate that into an already congested environment such as roads, pavements and such. The next one is looking at an advanced fault level monitor. Some people may be aware that through previous LCNF innovations, we've developed a reliable and robust mechanical fault level monitoring device to get active upstream and downstream contribution of the system. So hopefully looking to understand how it's going to change in the future. An active part of that is going to be in real time understanding and monitoring the fault level on the system, and being able to use that data to more accurately model our system, maintain and operate our system, as well as being able to offer flexibility connections to customers based on this. So what we're looking for is an advancement in how we can detect fault level on our network, and look at how we can more easily and accessibly integrate that over a multitude of different voltage levels from the LV up to our 132 kV network. And in an ideal world, would have a small form factor technology that could provide that at all voltage levels. So that's what we're looking for on that challenge. And then the last one, also relating to the charging of vehicles and looking at public charging infrastructure specifically. So it was touched on about HGVs and LVs and buses and taxis, where there's potentially requirements for dense charging capability at bus depots or taxi ranks, pods in the future around autonomous vehicles. What do we need, and how are we going to most efficiently install infrastructure to enable that? Both the infrastructure back onto the main parts of our network in the increases, and then the localized infrastructure to facilitate the charging. So they're the overview of the 4 themes. In terms of what we're looking for in scales of projects, as I'm sure people are aware, there's a wide range of Network Innovation Allowance existing projects and other incentive mechanisms for innovation. And what we're really looking for is either any of those 3 types of projects. So a small value, shorter time period feasibility piece of work to understand the needs, benefits and value of doing such a project, an isolated single performance trial in a localized area, and then a wider system approach of how we'd look to encompass a more network complete solution. And what we expect from those is the greater the depth and the greater the detail in a project, the greater the complexity, cost and delivery timescales. So in terms of costs and project value, would be looking for projects around the feasibility of in the range of 100,000 all the way up through to a full system integration approach of around £2.5 million. So that's the sort of scope that we're looking for. And then really just to conclude, so if you think you've got a solution or a potential solution or a methodology that can provide an answer, or at least improve our body of knowledge and take the learning forwards on either of those 4 themes, we have a live Google form at the moment, which we're looking to capture all responses, which closes on the 1st of March. Again, when the slides are made available, you can click straight to that from there. And what we're really looking for is clear and defined projects. So understanding what's going to happen, detailing the specific deliverables, outputs and outcomes, and how they're going to be achieved. And most importantly, we're keen for these to be direct third-party led projects. So we're looking to be provided evidence that there's the capability and capacity within the organisation or the set of organisations, if it's a collaborative approach, to manage and deliver the project from outset to conclusion. So I just wanted to spend a few minutes providing that overview, and yeah, thanks for listening.
Thank you very much for that, John. I hope that was informative for all of you listening. We have a chance now for us to take any questions for any of our panel members, so feel free to send them in using the functionality on GoToWebinar. The first one that I will answer myself is, will the presentation files and slides be made available to the audience afterwards? Yes, that is something we're going to do. We're going to put the slides and a recording of this webinar on our website shortly after the webinar is finished. Our website for network strategy is due to be changed in the not too distant future, so there may be a slight rejigging of pages, but we will send a link when that is available. So yeah, please feel free to send in any further questions. We'll wait for 20-30 seconds just for a few to come through. Thank you.
Hi, so yeah, I think we've got a couple relating to the NIA process, so I'll take a couple. To what extent does a consortia have to be developed at the initial submission stage for the 1st of March? And then the second one is providing an outline of the processes for the companies new to the NIA core process. So the first one is, would be looking for an element of understanding, if it's a consortium approach to a new project, of who was going to take what role and how that was going to be delivered. We're not looking for there to be any commercial agreements in place or anything like that, but a clearer idea who's going to do what and which and provide what value to the outputs and outcomes, I think could be useful. And then in terms of an outline on the process, so once you do click on the Google form, hopefully it gives you a relatively detailed explanation of what to do beyond the 1st of March. So we'll obviously receive the applications and take a view and review those and score them. And then after a period of time, we'll be looking to set up face-to-face meetings with the projects that both meet the NIA governance and hit the requirements of our challenges, discuss the project in a little bit more detail, and then, if successful, look to work collaboratively with that organisation or set of organisations to deliver the project to registration through the projectability assessment form through the ENA Smarter Networks portal. So hopefully that answers those questions.
Hello, it's Clive Goodman here. We've had a question within fault level monitoring. Has any thought been given to collating information from different sources? Yeah, it's a good question, and I think there's still some further work we can do on fault level monitoring. This sort of exercise, I think, was very much an initial start. But yeah, thank you for the question.
Okay, thank you, Clive. Holly here. Another question about the forecasts for WPD. It says, do you publish forecasts for WPD areas specifically for growth in various technologies, EVs, heat pumps, storage, etc.? In our distribution FES scenarios, we are able to share the megawatt profile and growth figures, which is the absolute numbers with a profile applied at winter peak demand. But we would be happy to share data on our forecasts for specific electricity supply areas. They're known as small geographic areas, if that's something we can collaborate with.
Hi, it's John again. A couple more around the NIA process, so I'll try and pick these up. Somebody's asked if the NIA is 100% funded. So the way the mechanism works is the NIA is 90% funding of the project, and the other 10% notionally comes from the hosting network operator. We're always looking for partner contributions, but essentially for the project value is 100% funded to the third party. But as I say, we'd look to encourage third party contributions to the overall value of the project to bring some work to it. Another one, looking at about applicants discussing project ideas with us prior to the submission. I guess what we're looking for is to use the Google form process to capture those ideas and look to come in. I think would be happy with relatively short informal discussions, but as I mentioned last time, we had over 80 applications, so in terms of the numbers and volumes, we're really looking to coordinate that and drive it through the Google form. And then I think the last one is looking at how will any project risks fall all on the third party or shared with WPD in some way. So this would really be dependent on what type of project it was, whether we were looking to do installation of equipment into the network or it was a feasibility study. There'd be a sensible approach taken looking to share the risks and the rewards of delivering one of these projects. Oh, and another one. Yeah, can you save work and come back to it? I think you can save a form and then go back to it partway through, and also building on that around the submission of a two-minute video. Whilst we think it would be really useful to get that video and it's a really good way to communicate what's happening and what you're proposing to us. If you're not able to do the video, and we appreciate for a number of reasons that might not be possible, what we'd look for is up to a maximum of a two-page A4 or a couple of slides to provide us a bit more detail, perhaps any pictures that you'd look to sort of bring the project idea to life.
Right, okay, thank you for that, John. We've got a couple more questions, but we will endeavour to send answers as we're just about out of time. So we will send answers to the questions that have been sent that we haven't been able to get around to answering. So all that leaves me to do is thank you very much for listening to the webinar today. If you've got any further collaboration with the network strategy side of things, there is our address, email, by post, by email, and the website address there for the network strategy pages. So I'd like to thank you all for listening and hope that it was a useful and a useful webinar. So thank you for attending and have a nice weekend all.